So I'm the only one teaching it.
Okay, good.
In the classes.
So in the spirit of complete and full transparency, I must admit to a whoopsie because I had homework 6.3. It's whoopsies all around. It's whoopsies all around. So I had homework 6.3 prepared. I had it ready. And then I got an email from Mr. Foster because he said, hey, are you going to post it? And it was there, and I just didn't turn it on. Whoops. So what I'm going to do is I'm going to extend that one, homework 6.3, to where it's due on Wednesday. And then homework 6.4 will be due on Friday. And then that'll actually get us back on track. So you all had a weekend without homework.
What'd you say?
You had a weekend without homework.
Oh, yes.
The last
You
weekend.
asked me something specific.
No. You had a weekend without homework last weekend. So yeah, I'm about like halfway done with exam 6-2. I actually, surprisingly, don't really have any meetings scheduled today. All my advising and registration issues were out last week. So I'm basically just going to lock myself in my office today until I get it done graded and distribute grade reports and whatnot. So when I say goal Monday, I mean it. That's my goal today. So, okay. Today what we're going to do, though, is we're going to discuss discretely braced beams in some more significant detail. And we're going to talk about the phenomenon of lateral torsional buckling. And the star of the show ultimately today is going to be this term CB, okay? But it's going to take me a while to sort of explain what CB even is and what it's for. And so we are going to go around the bend a little bit until we actually get to what CB is. So I would ask, give me a little bit of latitude on explaining what this is and what LTB is, but that's going to be our goal for today. Okay. Before I move on, did everybody get the QR code? Okay. All right. So let's start with some math. Okay. And I don't incorporate advanced level math in an applied class like this unless it's necessary, unless it's useful. And so there's been two instances where I've had to break out the wonderful world of calculus, and one of them was column buckling, and the other is this one. Okay. And so I want to talk about how beams buckle. Okay. And beam buckling is going to be the result of a solution of a differential equation, although that differential equation is much more challenging than the differential equation for columns. Say what you will, but the diffeq that we needed to solve for column buckling was actually pretty straightforward because all it was just the second derivative of deflection plus some constant times y equals 0. Say what you will, but that is something that you probably reviewed in Math 335, the solution of an equation that's kind of like this. The one that we're going to do for beams is a little bit more challenging than this. It's a little bit more involved. Okay. Now, in order to set the stage for what we're going to do, to be clear, this is not Math 335. I'm not going to make you solve diffeqs, but I do want you to have kind of an idea of what we're doing and why we're doing it. So I've got two calculus problems here on the board, and they're going to show up in a slide here in a second. But let's see if you all can help me out with this. So I have the derivative of 5 times the sine of x. So can somebody tell me what the derivative of that is? 5 times the cosine of x. Okay? Is everybody in agreement with that? So if that's the case, that's true, right? Everybody's shaking their head no, right? Why is this not true? Because this involves a constant times a function. This involves a function times a function. So we got to break out the product rule, right? Right? First times the derivative of the second plus the second times the derivative, plus the second times the derivative of the first, right? What's that? But you get the point, right? Okay? In general, the point that I want to make with these two derivatives is the idea of these multipliers. Okay? I want to make a point that when we're dealing with coefficients, whether or not those coefficients are constant or whether or not their variable changes how we solve a differential equation. Now I'm using a really simple example, but for those of you in differential equations, you could tell me that if I had y double prime minus 4y equals 0. I mean, I'm sure you all are having all sorts of fun in Diffie-Q, but admittedly, this is a pretty straightforward Diffie-Q to solve. But the moment that I take this 4 and I turn it into 4 tangent of x squared, that does change things a little bit. That changes the method by which we solve the Diffie-Q, and it makes the solution and the problem that much more challenging. Make sense? So I just want you to keep that thought sort of in the back of your head. Now I am going to throw, here's my warning, my disclaimer that we are going to see some calculus, we are going to see some differential equations in the next few slides. I want to be clear, I'm not making you do any of this on a homework or an exam. I'm not making you do any of the calculus, so y'all can relax there. But it's just meant to highlight some of the problems that we're going to deal with in our differential equation solution. To sort of highlight on a common theme, if you remember when we did column buckling, I gave you this nice pretty solution to a differential equation, and then I told you why that solution didn't work, right? I'm going to do the same thing with beams, by the way. So I would say that the beam buckling equation has more utility than the column one, but even then there are some things that we need to change. Okay, so, all right, let's go back to big picture, okay? I said that a while back that we're ultimately going to solve or learn how to analyze and design continuously braced beams and analyze and design discretely braced beams. And I said, if you know how to analyze and design a discretely braced beam, then you know how to do it for a continuously braced beam. Because a continuously braced beam is just a discretely braced beam where LB is 0. So discretely braced beams are the more general case of design, okay? So really all we've looked at are discretely braced beams with an LB of 0. And we know that if LB equals 0, then the nominal capacity equals MP. We've already discussed that. I'm hoping by now this part right here is pretty clear. Everybody okay with this? So now I want to discuss what happens when LB is bigger than 0. And if LB is bigger than 0, we got to figure out what MN is. Okay? Now remember, here's a beam. There is a big difference between the unbraced length and the span length. So a beam might be 30 foot long, but the distance between braces might only be 10 feet. Okay? And the idea is that this is the value that affects your structural analysis a little bit more. This one's the value that affects your capacity and your design a little bit more. So just keep that in mind. Okay, so beams buckle. Okay, why do they buckle? Okay, so if I have a beam, let's say a W shape, and it's under sort of a positive bending type effect where the top's in compression, the bottom's in tension, that presents a stability problem. Okay. Because the thing is, the top being in compression wants to buckle, but the part that's in tension doesn't want to buckle, okay? And the beam doesn't really know what to do. It's got a hard time figuring out how is it going to resolve that. The fact that some of it wants to buckle and some of it doesn't. And the only way that a beam can resolve that physics problem is it does this thing where the beam sort of kicks out and it twists, okay? And we call that lateral torsional buckling, and it experiences this sudden lateral deflection and this twisting effect. I've got a couple of examples in the real world. So first off, I have here, this is a lab test, which you all can, I've got the link right here, you all can pull that up, and I've got the notes on Blackboard, so you all can pull that up to your heart's content. It shows what happens when you take a beam and you load it, and you can see this sort of kick out and twisting effect. You could also, like as you're watching the video, maybe speed up the time lapse and whatnot and really kind of see it go, boo, go like that. It's pretty cool. This one, maybe not so cool because this is in the real world. This is from a bridge that was in Canada in around 2015. And you can see what had happened is as they were erecting the structure, it was being subjected to its own self-weight. And you can see what happened. These really large plate girder elements kicked out and twisted. And so you can also see, like, look what it did to the braces. I mean, those braces are just gnarled messes, right? these buckling phenomenon, they can generate a lot of forces inside those braces, and so these braces obviously didn't have the required stiffness in order to restrain that, and the girder just went. Okay, so this is just an example of the type of phenomenon that you're seeing. Okay, and this is a buckling type effect. And one thing I will say is that if you kind of look at the shape, see how this kind of looks a little bit like a trig wave? So you can imagine that we're going to have a little bit of that type of math show up in our solution. Okay. Everybody with me so far? Okay, so now, so the next few slides are going to be pretty math heavy and pretty mechanics heavy. Just sort of bear with me. Okay, so the first thing I want to do is I want to talk about torsion. Okay, so the name of the phenomenon is lateral torsional buckling. So let's talk a little bit about the torsion. Okay, now everybody in here had a course, Engineering 216, Mechanics of Materials, Mechanics of Deformable Bodies. Everybody in here took that class. Okay, and it's probably been a while since you had that class, but one thing I will sort of refresh your memory on, I know either when I teach it or maybe when Dr. Zakar teaches it, there is a section of the class that's on torsion. Okay, and if you go back to your notes and go back to that section of the course where you were discussing torsion, take a look at your notes, take a look at the problems that you did, take a look at the questions that were on the exam. And I would bet money that the vast majority of you were dealing with torsional problems where the cross-section was circular. Okay, in other words, the element that was being twisted was either some sort of solid circular shaft or it was a pipe. Okay, some sort of pipe element that was being twisted. Okay, and that's not that unheard of. I mean, in most mechanical design, if you've got something that's being twisted, chances are you want it to be a circular cross section because circular cross sections resist torsion more efficiently than other sections. Am I right? My mechanical in here, he concurs with me on that. Okay, now let's go back to that mechanics, that math. Okay, so this right here should be something that you remember from Engineering 216. The idea that if I have a circular section and I apply a torsional moment or a twisting moment to it, I can calculate angle, that angle phi, that angle of twist, how much it goes from here to here, the angular angle of twist, as TL over GJ. Okay, T being torsional moment, L being the length, G being a material property, kind of like E, a shear modulus, and J being a polar moment of inertia. Everybody remember that for circular cross sections? Or if you wanted to write it in DiffyQ land, you could say that the torsion equals GJ times the rate of twist. Okay, all right. Is this part familiar? Everybody familiar with that? Okay. Now, there is another reason why we tend to utilize circular sections in most mechanical design components where we've got twisting, and that's because of the presence and the impact of warping. Okay, so if you have a circular cross section, so let's say I have a pipe. Okay, we'll use this marker as an example. Okay, if you have a pipe and you apply a torsional moment to it, what happens is the circular cross section, it rotates, but that's all it does. If the cross section is circular, the only way that it deforms is it just rotates. But if the cross section is non-circular, that's not the case. So for example, if I was, instead of twisting this circular marker, if I was twisting this, let's say, eraser, okay, not only would the cross section rotate, but it would do what's called warping. So non-circular cross sections will rotate, but they'll also deform in and out of the plane. Okay? So if you take an I shape, and you twist it, not only will it rotate, but the flanges will go in and out. Okay? The flange tips will rotate out and rotate in. So like if you cut a cross section here and here and here, you're getting these deformations in and out of the plane of the cross section. Does that kind of make sense, that visual? Okay, that's called warping. Okay, circular cross sections don't warp, but non-circular cross sections, like I don't know, an I shape, they do warp. Okay, so this differential equation does not hold true for non-circular cross sections. In fact, a more generic version of this cross section would look something like this. So for a circular cross section, we have the torsion equals GJ times the first derivative. Now we've got the torsion equals GJ times the first derivative minus all of this, okay? And so the idea is that that torsional response is a function of however much the section is rotating and however much the section is warping, okay? Now, if you want, I'm happy to get into the derivation of how you get a third derivative and what C sub W is. We can go down the rabbit hole on that, but I'll say a couple of things to maybe shed some light on what's going on. So first off, if you look at the flanges are going in and out of the cross section. So along the section, the flanges are almost experiencing like a shear, okay? Do you see how that, like, one side's going up, one side's going down? It's almost like the flange is being sheared, okay? So that's why there's a third derivative. So if you have a deformation, the first derivative of that is related to its slope. The second derivative is related to the moment, right? That's why we have the second derivative is m over EI, right? Okay? Well, the third derivative would be the shear over EI, because then the fourth derivative would be the loads, okay? So whenever you see a third derivative of deformations, chances are there's not really chances are, almost like a direct relationship between that and shear, which is why there's a third derivative. Okay, so that's why that's there. Because of the math, what I'll tell you is that this C sub W term, we don't really use it very often because we can get around it with some other terms in steel design, but it has units inches to the sixth. So just, yeah. Again, like moment of inertia has inches to the fourth, and that really doesn't make much spatial sense either, because we don't really live in a fourth dimension. But really what it is it's like an area times a distance squared. So it's sort of the same idea with the C sub W. Okay, so to put things in perspective with what we're about to do, and again, I'm not gonna like go down the rabbit hole on this, but if you want, I can. I've got a fully fleshed derivation I'm happy to provide you. But just to put things in perspective, when we were dealing with column buckling, all we had was this differential equation, like y double prime plus this term times y equals 0, and from that we got this, right? That was our goal. We have a second derivative, or a second order differential equation, and from that we're trying to figure out the load that causes buckling. Well, with beam buckling, we don't have one diffie we have to solve, we sort of have three, okay? Because think about what's going on as the beam is buckling. Okay, well, first off, I'm going to work backwards. There's the twisting, right? Because as it's buckling, the element is twisting. So we've got this impact going on. The second is it's not only twisting, but it's kicking out and twisting. So the beam is deflecting this way. So there's this m over EI term that way as well. But then what causes the buckling to begin with? What causes the beam to kick out and twist? It's the fact that you're stacking load on top of it. So the beam's just deflecting vertically in a very normal fashion as well. So there's a lot going on all at once, okay? The way that we solve this diffie is we basically make some substitutions, like we substitute some of these differential equations into their counterparts. And after we substitute and simplify a little bit, we get this, okay? I know this is kind of a messy equation right here. So this is ECW times the fourth derivative minus GJ times the second derivative plus this term times the function itself equals 0. By the way, our differential equation now is not written in terms of deflections, but it's written in terms of the angle of rotation, okay? So, all right, so we get this differential equation, and from that we solve and we get this. And very much akin to how we did this one, we took this differential equation, solve to get that. We're going to take this differential equation, solve it to get this moment that causes buckling, okay? Again, I'm happy to get into the math of it, but I'm hoping that based on what we did in more explicit detail with column buckling, that you can sort of follow the analogy with beam buckling. Everybody with me so far? Now, like with column buckling, I told you that the solution had a problem. This one has a problem too, okay? And the problem with this solution goes back to these derivatives I brought up at the very beginning of the lecture. Okay. Let me go back. I want to go back to this this slide. Okay, because I want everybody to sort of follow along with me on this. Okay. So the differential equation that we're solving for is this. Let me write that differential equation down. So we have ECW times a fourth derivative. So if you want to write it like that, you can. Minus GJ times a second derivative plus, and then we have m squared over EI. In this case, EI to y, because it's deflecting laterally, times phi is 0. Okay, so this is the differential equation that we want to solve. Okay, now let me go back to this derivative right here. Okay, the derivative of 5 times the sine of x is 5 times the cosine of x. So really all we did is we factored out the 5. And we took the derivative, right? Why were we allowed to factor out the 5? Because it's a constant, right? Okay, so let me ask a question about this. And let's just think about it in those terms. Could we factor out E? What is E?
29,000.
Sounds like a constant to me, right? So does this pass the constant test? You bet. Same thing right here. What about for a given beam? Okay, you can open up the table of W shapes right now. If I were to give you a W24 by 76, is the CW value a constant? Looks like a number to me, right? So is CW a constant? Yep. Is J a constant?
Yes.
Looks like a number to me. What about G? Well, if E is a constant, G is a constant too. This is a material quantity. That's a constant. Is IY a constant?
Yes.
All right. So here's the thing. While this differential equation looks pretty nasty, okay, when you all took DiffEq, if you were given this problem, could you solve it? Chances are you probably did problems like this in Math 335. I'm almost positive you did. And what I'm saying is that this problem and this one are pretty much the same, right? So what do we have? So this has a 1 here. Constant, 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 constant. Wait a minute. I conveniently didn't talk about that, did I? I didn't talk about the moment. Is the moment a constant along a beam? That's the problem. How many moment diagrams did we deal with last semester that looked like that? Did we really have any problems like that in CE 312? Not really, right? Moment diagrams are like this, or like that, or some sort of shape to them, right? Okay. In other words, the problem with this solution that I came up with is this solution is fine as long as moment is constant. At the exact point that moment becomes a variable, that solution gets out of whack real fast. Okay? All right, think about it. Like, this differential equation looks complicated enough as is, all right? Now imagine if that's a variable. That just becomes ridiculous to solve. Okay? So much so that we engineers recognize that and we get around that with a very specific term. How do we get around that? With this. Okay? So let's talk about CB. Okay? So what is CB? CB is what we call a moment gradient modifier. Okay? Now the purpose of CB is to recognize the fact that this is what moment diagrams really look like. Okay? And I propose that because moment diagrams are in fact variable, we must account for that in some fashion with the solution that we have to predict beam buckling. And that's what CB is. Okay? So what is CB? It is a moment gradient modifier. If you want a way of thinking about CB, this is not correct, but there's an analogy to it. CB is sort of like the slope of the moment diagram. The more the moment diagram changes within a given range, the more the moment diagram changes, the higher the CB term is going to be. Also, if you're dealing with a region where all the moments are the same, then CB will be 1 because there is uniform moment. It's not changing at all. Okay. So what does CB do? CB changes the solution to our problem by accounting for the fact that the moment is in fact variable. Okay. So there's a couple things that you need to be aware of when using CB. Okay. So first off, CB is calculated as this fraction. Okay. Every term that goes into CB, the MA, the MB, the MC, the MMax, are taken as absolute values. Okay. So whatever the value is on the moment diagram, if it's up here, it's down here, you take it as an absolute value. What you do is that within a given unbraced segment, so let's say this is an unbraced segment, what you do is you split it up into quarter points. So if this segment is 20 foot long, take a value at every 5 foot, at 5 foot, 10 foot, 15 foot, and those are going to be your quarter point moments. So we'll call those MA, MB, and MC. And by the way, it doesn't matter if you go A, B, C, or the other way, go A, B, and C, because you're doing the same thing to A and C. It doesn't really matter. So you can go left to right, right to left, doesn't matter. Okay? You also, within that segment, take the absolute worst case moment. So the worst case moment could be on the ends. It could be one of these. So in this case, it's MB. Or it could just be somewhere else. You take the worst case segment and you plug and chug. Okay? Now, this is sort of like how CB works, but I think the best way of doing this is to go through an example. Okay? So like I said, our goal today is to make sure that we understand CB. Okay? So I went through and I did a bunch of math and I showed you some solutions to beam buckling. What we're going to do on Wednesday is we're going to say, okay, now that we've discussed CB, and we kind of understand the math of it, we're then going to present the be-all, big picture, here's how you calculate beam capacity, and that's what we'll do on Wednesday. But today, what I want to do is I want to focus on this CB term. It's not difficult, but it does warrant its own sort of separate discussion and separate consideration, as it were. Okay? So I'm giving you a beam, okay, and this beam is 45 foot long. What is LB for this beam? 15 feet. That's the distance between braces. Now, I could have this segment be 20 and this be 10. There's nothing stopping that. But for the sake of discussion, every segment has an unbraced length of 15 feet. Okay? Now, I've given you that this beam has a distributed load of 2 kips per foot. We're going to assume that the loads are already factored, so we don't have to worry about that. And that factored load also includes the beam self-weight. So we don't have to worry about the load factoring or anything like that. All that's taken care of. Okay? Now, I already did some structural analysis for you. I gave you some reactions here. And then, so what would the shear diagram look like for this beam? It would go up, it would go down, go back up, and go like that, right? So this is the shear diagram. Okay? We're not actually really going to use the shear diagram for this beam, but if we wanted to, or for this problem, we're going to use the moment diagram. We need the shear diagram to get the moment diagram, but we're not going to really use this directly. The only comment I would make is that if I was in analysis and design mode, if I was trying to assess whether or not this beam had capacity for shear, what I would do is I would pick the worst case value on the shear diagram. In other words, I would pick this. I would just take my shear to be 37.5 kips and make sure the beam has enough capacity for that. Although at this point, I think we know that that's probably not going to be an issue with W shapes. They just kind of have shear capacity. It's not a problem. Now here's the moment diagram. So the moment diagram is sort of like this, and then it goes like that. Now where do I get these peak values? They come from, the area of the shear diagram. So what do? I go a lot to a little to a lot to a little, right? So that's how I'm getting this. And this is my moment diagram, okay? So the other thing I'll say is that these vertical lines right here, this vertical line here and vertical line here, that's where the braces are, right? Because I've got a brace here, 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 and here. So here, 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 and here. Those are my braces, okay? Does that make sense? Okay, So let's go back to CE 312. How many moment functions do I need to fully define this moment diagram? Don't remember that? How many parabolas? Two, right? So what we'll do is we'll cut a section like here, cut a section right here, and get some moment functions, right? So let's do that. Let's go back to 312. Okay. So what we're going to do is we're going to cut a section 1-1, section 2-2. Remember, for the purposes of structural analysis, sort of like, and so my goal right now is I'm trying to derive moment functions. Do these X braces affect that? Well, did they affect computing support reactions, drawing shear diagrams, drawing moment diagrams? No. So they don't affect the construction of these right here. So I'm just going to ignore them. Okay? So let's look at section 1-1. Now, if I'm cutting a section 1-1, which do you think is the easiest way to look, left or right? Left. So we'll look left here. How about section 2-2? Right. Moment functions. Okay. All right, so what do we see when we look to the left? We see a beam. How long is this, by the way? X, right? Because we're cutting a section at some distance X away. So, we're going to call this distance X. And honestly, same right here. Now, when we were in structural analysis last semester, we would have said, well, wait a minute, Dr. Mike, that's X of 1 and that's X of 2. I think you all get what I'm talking about at this point, so I'm going to keep things simple. So, okay. So, oops. All right, remember we have a shearing moment right there, right? This, we have a reaction here. This was given. Okay, go away. All right, so remember we said this dimension right here is X. And then, before I start writing equations, what do I do with this distributed load? We're bringing it back to CE 312, aren't we? Collapse that into a point load, and that is a point load of what magnitude? And then this dimension right here. So, right? Some moments at the cut, right? So obviously at the cut, we're going to have a moment, so we'll put that right here. Maybe I'll call that M1, since we are going to have an M1 and an M2. All right, so does the 22.5 cause moment? What side does it go on, left or right? At a moment arm of? X. X, so 22.5X. And then what about the 2x? Does it generate moment? Yes. Side of the table, left or right? At a moment arm of? So 2x. And then, what is that? 2x times x over 2 is x squared. Does that equation look right, by the way? 22.5x minus x squared, I mean, does that look right? It's a negative parabola that opens downward. Now this is valid from x equals 0 to x equals what? 30, right? Because it goes from, I mean, we're talking essentially about this parabola, you know, that goes from here to here, right? So is that fair? Is that fair? Okay. So how about section 2? We said section 2, we're going to look to the right. Is that what we said? So that's what it looks like, right? No reaction over here because we're talking about, you know, up here we're talking about cutting a section and looking that way. So the only thing we see is the beam and the distributed load. We don't see anything else. So this equation is going to be a lot easier because we don't have a reaction to deal with. Same story here. Same story there. So we have M2 and we have that. And this is going to be valid. So because we looked to the right, okay, we got to keep in mind that this is going to be valid from x equals 0, but it goes this way, right? So x equals 0 to x equals 15. I did this part kind of fast, but we've done this before, right? It's been a while, but we've done this. Okay, anybody have any questions on this? Okay, so forgive me, I'm going to screen capture this again. See if this behaves with me. I just don't want to have to keep scrolling. Okay. All right. So now that we've got our moment functions, let's see if we can do some figuring here. Okay. So we're going to be calculating moment gradient modifiers. Okay, and if you would permit me, okay, this is our moment diagram, okay, but this moment diagram corresponds to the following beam. And I'm going to try and draw this beam maybe to scale, okay? So, bless you. So we have a beam with distributed load on it. Okay? And so I'm trying to line that up like this. Now there are braces, right? Okay, so there are braces on the beam. Let's see. Right there. Right there. Right there. Right there. Okay? So the idea is that like this moment diagram here, here, here corresponds. Okay? Now, a couple things to point out. All right. Each of these segments are to be treated like independently. Okay? So in other words, LB is 15 feet. For each of them, but I claim that because each segment is subjected to a different array of moments, each segment has potentially, and in fact does have, a different CB value, and they're different from segment to segment. So we got to figure out what they are. Okay. Now, just to make sure we're all on the same page, we have M1 that, M2 is that. Okay? So the idea, just so we're clear, all right, so this would be 0, 1, 2, 3, 4, 5, all the way to 15. And just so we're correct on our math, what is 15 squared? Which is how we're getting this value, right? And if you plugged in 30 into this equation, you'll get that. And don't worry, we'll probably test that here in a bit. Okay? Now the other thing I'll say, just so that we're aware, because I'm going to start doing this here in a bit. If you take 15 feet and you divide it by 4, you get 3.75 feet. Okay. So far, so good? All right. Okay, so what we're going to do is we're going to look at each segment one at a time. So let's look at segment 1 first. Let's look at this segment. So let's see if we can figure out what CB is. Okay? So the way that this works is what we're going to do is we're going to find quarter point moments within this segment. So we're going to find what this term is. We'll call it MA. This term is MB, etc. Okay. So let me do this down here. So what I'm going to do is I'm going to plug in quantities for these distances in this first moment function, right? So MB is going to be M1 at X equals, so 15 over 4 is 3.75 feet. 2 quarters is going to be what, 7.5 feet? MC is M1 at X equals, what is that, 11.25? Did I do that right? 3 quarters. And so I'm basically plugging and chugging into that first expression. Why am I using the first equation? Because that first equation defines the moment diagram all the way across. Okay? So this is, let's see, 22.5 times 3.75 minus 3.75 squared. 22.5 times 7.5 minus 7.5 squared. 22.5 times 11.25 minus 11.25 squared. Y'all see what I'm doing here? I'm trying to figure out what the values are on that moment diagram at every quarter point. So just help me out with the first one. What do you get for this first one?
70.3125.
70.31, we'll say.
70.3125.
Okay, we'll just cut it off at 2 because that'll be fine for this. But is anybody else getting that? Okay. So for the second one, would you agree with me on this? 112.5, is that okay? And then the third one ends up being 126.56. So actually, if you scroll up here, this is MA, this is MB. This value right here, that's MC. Okay? And if we look at our scale, that's about 70, that's about 112, so that looks right. Okay? So is everybody seeing how we're figuring out quarter point moments? Okay. Now, the next thing we got to figure out is within segment 1, what is the biggest moment within segment 1? MC. So it just happens to be MC. That's very possible. Okay. So what we'll say is M max equals MC, which is 126.56. So if that's the case, once you get these 4 moments, CB, very plug and chug. Because the way you calculate CB is you got a big old denominator. All under that. Okay? So again, we just take everything as an absolute value, everything is a positive number, although that's not really a big deal for this segment because they're all positive anyways. All right? And what do we get for this? And again, part of this is just to get yourself familiar with the expression. That's really sort of the point here. I know we're running short on time, so. Anybody got a value for me on this?
1.165.
1.161.
65, sorry.
So we'll call it 1.16. Do I have a second on that?
Second.
Okay. So that right there, that's going to be our CB value for this segment. Okay. Okay. Everybody with me on that? Okay. So I'm going to really quickly do the remaining segments just to show you what we're going to do. So let's do segment 2. And segment 3 right here. So what we've got to do with segment 2 is, remember, we're still using the M1 function from here to here. So we got to figure out MA, MB, and MC. So that means we got to figure out MA, MB. Don't know yet if that's 0. It might be. MC and M max. What's M max going to be for this segment, by the way? If we're using absolute values for this segment. 225, right? Because we're using absolute values. Okay? So what we're going to do here is MA is going to be M1, MB, I'm going to use the M1 function, MC, I'm going to use the M1 function. But because that expression is valid through x equals 30, just keep using it at quarter points. And when you chug this out, you get 70.31. You get, this one is in fact 0. And this one is negative 98.44. But when you plug and chug into the CB expression, always use absolute values. So M max is negative 225. So this use absolute values. Now, I'm going to go ahead and give you what the CB expression is for this one. And this is more just, I want you to practice to make sure that you're comfortable with the expression. But when you chug it out, you're going to get that CB is 2.63, okay? And for segment 3, because we're running short on time, what I'm going to say is use M2 is minus x squared because that's on the other end. And when you chug this one out, you're going to get CB is 2.33. I want you to practice that one. Okay. Yes.
For the M2 equation, you start from x equals 0 again?
No, oh yeah, oh, this one, yes, you would start from x equals 0. But this one, you keep going with the other one, because that's the expression that we're using for that segment of the moment diagram. All right, does this sound good? Okay, so when we come in Wednesday, I'm going to talk, basically I'm just going to set the stage for beam capacity. When you see this CB term there, you'll kind of respect it. And I'll have 6.3 posted today, due Wednesday. That's all I got, everybody. I'm going to pull the QR code up one more time. I'll see you on Wednesday.